All right, so I did my research on studying collisions in blue white dwarf systems using N-body simulations. And presentation by me, Evan Wilson. I go to Pasadena High School, and my mentors were Valeria and Constantine over here. So, next slide. Okay, so table of contents. So what I'll go over today is what are white dwarfs and what is their pollution, what the goal of my project was, methods I used, the results I reached, and the conclusions I got. So first of all, we're going to go over what are white dwarfs and what is white dwarf pollution. So really quickly, as you can see kind of right here, this is the process of stars that they go through. So they're formed in a nebula, and they kind of go through this process. And we're right here, the star sun right now. And as it develops more, gravity, the stars are so massive that gravity tries to crush them inward, but nuclear fusion in their core kind of pushes outward, preventing them from being crushed in. So as this nuclear fusion kind of depletes, they go through a massive phase right here where they gain in size and then begin letting off material. And after that, gravity kind of wins and crushes them into a smaller star over there known as white dwarf. In these white dwarfs, we expect to, in these white dwarfs, we expect to only see helium and hydrogen in their atmosphere because they're so dense that any other elements we would expect the gravity should draw them into the star. However, that's not what we see. We actually do see other elements. There's carbon and oxygen. Now, Valeria and Constantine expect this to be due to collisions from asteroids that are orbiting the white dwarfs, and when they collide, they release dust and other particles that kind of float down to the surface, and that's what they see. So the goal of my project. This formula that you see right here, N sigma V, is used to calculate the predicted amount of collisions for a particle per unit of time, which is also known as collision frequency. So in this formula, N right here represents the number density of particles in the system. Sigma represents the particle's cross-section, and V represents the particle's average relative velocity. And this formula is used in a lot of fields of astrophysics and astronomy to calculate the predicted amount of collisions for a particle. However, when Valeria and Constantine used it, as you can see right here, there's a discrepancy between the theory, what they predicted would happen, and what the simulation told them happened. So my project was kind of to see what may cause this and if this was a legitimate issue. So the methods that I used. When you're using N-body codes, there's usually two standard things for orbital dynamic problems. There's rebound, which is a package in Python, and there's Mercury from Fortran, an old programming language. So initially, I was using rebound, which you'll see some plots from later on. But the issue with rebound is that it runs very slow. So if you're trying to use a lot of particles, simulate a lot of particles, it'll take a really long time. One of my simulations took days to run, and I didn't have that kind of time. So I switched over to Mercury, and in using Mercury, I used one of Valeria's Jupyter notebooks to create input files necessary for Mercury to run simulations. Now, in these input files, among other orbital elements, I specified the number of bodies, what their radius would be, their semi-major axis, and their eccentricities. So when running these simulations, this is kind of a picture of using GEHUM right here, which is Mercury, the one just talking about here. So GEHUM's a remote machine used by Constantine's group at Caltech to run simulations. To access it, you go in through command prompt on your computer and use Linux commands to bring in all the files and run simulations. So here's the results I got after I ran the simulations. This is a picture of the rebound plots that I was talking about earlier. These are produced by Jupyter Notebook. So as you can see, each of these little dots right here is a particle orbiting what we simulate as white dwarf. And these are all, this one, and this one are all 3 separate simulations. I'm showing examples of what rebound looks like. Now, this is what I used for the majority of my project. This is the info that GitHub gave me. So I ran over 60 simulations and collected the information from GitHub and put it into some graphs, or into a Google Sheet first, and then into graphs later. So in the Google Sheet, you can kind of see all the work that I did. So these are the titles of all the columns where I put all the information. So number of bodies right here, radius, centimeter axis, eccentricity, sigma, the cross-sectional area of the asteroids, the average velocity of the asteroids, the number density of the asteroids, and the predicted time for a collision to occur, which is the collision time scale, the number of collisions, and what and the average time for a collision to occur in the simulations. So after taking all that data, I plotted some numbers against each other. So first was collision time scale versus the number density of asteroids. And up here you can see the theoretical collision time scale, which is the reciprocal of n sigma v. So in that, as you can see the number density right here, so we would expect as the number density gets larger, the denominator grows, and we would expect the collision time scale to shrink in return. However, so that's what we plotted right here. However, the simulation showed that there was much less of a dependence on number density than we expected. So next was the dependence on radius. So as you can see, sigma also in the denominator. As the radius grows, we would also expect the collision time scale to decrease. However, when increasing the radius, as you can see right here, 100-kilometer radius, we got 7 collisions. After we increased the radius to 500 and 1,000 kilometers, we got 0 collisions for both, which was really unexpected. And as of now, we don't know if that was an error with the code or something unknown with the system that we don't know yet, but that definitely requires further investigation. So, as I said earlier, I would also add eccentricity of the asteroids orbiting the white dwarf. So, if you don't know what eccentricity is, there's kind of an example up here. An eccentricity of 0 is an orbit of perfect circle, and as the eccentricity increases, the orbit becomes more elliptical. So an eccentricity of 0.95 looks like that. This one, our theory was pretty close to what the simulation predicted. So as in a very highly eccentric orbit, the particle will move faster as it gets closer to the star and slower as it gets farther away. So as it moves faster when it's closer to the star, there'll be more chances for it to collide with other objects, which is why a higher eccentricity we predicted would lead to lower collision time scale. And for this one, the theory was close to what the simulation gave us. So my conclusions is there do continue to be discrepancies between the n sigma v formula and our theory and the simulations. The strangest of these theories was that the simulation collision time scale was almost independent from number density. Also strange was that the size of the asteroids, as we increased the size of the asteroids, there were 0 collisions, which we still don't know what the reason for that was. But what did match was that bodies with more eccentric orbits collide more often than lower eccentric orbits. And I just want to thank my mentors, Constantine. It's a really cool picture, by the way, and Valeria. So thank you both of you for all the help you gave me.
Any questions for Evan? We learned a lot of astronomy this afternoon, so. Any questions?
So what are the computational requirements to run the code in terms of, is it a laptop job or is it a people processing?
So on my laptop, I was remotely accessing the Batygin server, which is at Caltech. I don't know a lot of the details. Constantine mostly uses it, so you can ask him for some specifics, but it's not about the hardware that you were using, because you remotely access the server. So I just uploaded all the files that I have for the simulations.
You mentioned that the Python library was a lot slower than the Fortran library. What makes, what is the reason for that?
I didn't go into that a lot, but mostly I just used the Python library for simulations with 1 or 2 bodies. I'm not really sure why it ran slow. I think because that's using more of your hardware, and while the Fortran uses a server here at Caltech, which is a lot more faster. On my laptop.
What do you consider your biggest surprise over the summer? What was the most unexpected thing about?
Definitely was that when increasing the size of the asteroids orbiting the white dwarf, we got less collisions. Because you would expect that if there's say there's 10 bodies orbiting a star, you would expect that if you make those bodies larger, they would collide more often, just because they're taking up more space. But that's not what we encountered. So it could be an error with code, or it could be something else that we don't know. Thank you.
So I have a question. So you've done a number of our summer programs over the last few summers.
Yeah.
Typically, you're in a group. Today, this year, you happen to be in a one-person group. How was that, not having collaborators? So you were really working directly with the mentors, but not other peers.
It was a lot more difficult, but it was also a lot more informative. So, one of the issues was I was on vacation for about 10 days during the summer. And if I was in a group, that wouldn't have been such a big deal, because one of my group mates might have been able to pick up the slack that I left while I was gone, and then I could have helped them out more when I got back. But when I, since I was kind of individual on this, by the time I got back, all my work had kind of piled up, and I had to work overtime to get done.
Got it.
Yeah, I did.